Mr. T here. This is Packet 12, Gases, Chapter 11. This packet focuses exclusively on gases. We'll talk about the theory of gases and some properties of them. Then we'll start focusing on gases in various environments. Um, we summarize it as an open container, closed container, as well as a closed expanding container. We'll talk about the properties of the gases in these various types of containers, um, as well as gas laws and various types of equations representing those gas laws, which you will then memorize and practice doing gas law calculations. We'll then talk about gas calculations involving stoichiometry again, where we go from moles to something called molar volume, and that's the amount of volume in liters of gas. First thing we're going to address is the kinetic molecular theory of matter, and it's just a series of 5 statements talking about the properties, the physical state of gases. Now, you see a fixed container right here, and it contains gas particles. They're not attracted to each other. They just fly in specific directions until they hit the surface of the container, and then they bounce. Now, this looks very similar to collision theory, where you had bouncing particles that would collide, and then a chemical reaction would occur. This is a simplified form where they bounce. They don't actually chemically react. They just bounce off of each other, or they bounce off the walls of the container. So these 5 statements should be pretty straightforward. First one, matter is composed of tiny particles such as atoms or molecules or ions. The particles have movement, and movement, another word for movement is either temperature or kinetic energy. And then particles can interact with each other than physically bouncing. If you have a negatively charged particle, such as a chloride ion, which I'm circling right here, and another negatively charged chloride gas particle, like charges repulse each other. They don't like to be near each other, so there can be repulsive forces. So gas particles technically can push each other away without actually touching each other. Conversely, you can have a positive sodium ion gas particle that's floating around and a negative chloride ion gas particle, and then when they fly, even if they're not directly at each other, they may shift toward each other because like charges are attracted to each other. So that's why this next statement, particles interact with other particles cohesively and repulsively. Just talked about temperature as movement. So kinetic energy and temperature is movement. Please do not confuse kinetic energy with heat. Heat is the gasoline. It's the energy that powers the movement of particles. Whereas kinetic energy is just the movement. And temperature is another word for kinetic energy. It's actually the sum of all kinetic energy of all particles in a substance. Or you can just summarize it as this. Temperature is movement. And then when particles actually do hit each other, so here's one particle. Well, that's a bad drawing. Let's do it again. Here's one particle, here's another particle, and when they do hit each other, they're going to bounce off each other like pool balls on a pool table. Now, there's different types of particles bouncing against each other. You can have particles where they're very rigid. So think of a boy in the mountains, and he's throwing an ice ball. That's very rigid, and it's going to hurt his little brother if it bounces off. So anything that has a perfect bounce we call elastic. Now, if you were to sit there and have a snowball would actually crumble away. So there's the little brother, there's the big brother, and the little brother throws a snowball, and then what happens is the snowball breaks up into tiny little pieces. So if it deforms or breaks, we call it inelastic. We're going to assume for gases at this level that they're going to be mostly elastic collisions. Why? Well, because by saying this, it makes the concepts and the math a little bit easier. Now, we have disruptive and cohesive forces that are present in gases. Cohesive forces promote particle interactions. So, for example, I talked about sodium and chloride gas particles, and they may be attracted to each other even if they are not directly aligned toward each other to hit each other. They may move toward each other because like charges repulse. And disruptive forces would be two gas particles that have the same charges, and they're going to be repulsed away from each other. So that's what we call electrostatics. They're both cohesive and repulsive, depending on whether they're positive or negative. There's other types of disruptive forces. Temperature is considered a disruptive force. So temperature is movement. So the faster the movement, the faster the gas particles are going to be moving around, and they're not going to have a chance to be attracted to another gas particle because they're moving around so fast. And then there's something called friction. So whenever you have a bunch of particles close together, as particles bounce, they rub against each other. So that's my attempt to show rubbing. And then it will dislodge particles and make them bounce even more. So we're going to go ahead and apply the concept of disruptive and cohesive in the three states of matter, also known as the three phases of matter: solid, liquid, and gas. So please do me a favor. Know these 5 statements for the kinetic molecular theory of water. Excuse me, of kinetic molecular theory of matter. You don't have to memorize, so you don't have to memorize each of the sentences word for word. Just be familiar with it. You could see it on a multiple choice question, for example. And then you need to be able to apply these statements right here in a question like slide 5, which is really easy in my opinion. So for example, here you have a solid, here you have a liquid, here you have a gas. If the cohesive forces are keeping the particles really close together because they're really attracted to each other, it's dominant cohesive, then it's going to be a solid. On the other hand, if it's a mixture of cohesive and repulsive, the particles are attracted to each other, like opposite charges attracting, but yet there's temperature which is causing them to fly away from each other. If it's in equilibrium, it's a liquid. On the other hand, if it's mostly disruptive forces, you have a lot of temperature and they're moving really fast, and they don't have a chance to be attracted to each other, then it's considered a gas. So make sure you have those down. I could ask you a question like this. For example, if the substance molecules possess cohesive forces which are overall lesser, so the dominant one's going to be disruptive, therefore the answer is going to be the physical state is probably going to be in as a gas. So in general, if we go ahead and we increase the temperature, we're increasing the disruptive forces, and it goes from a solid to liquid to gas. Now we're going to get into something called gas laws. These gas laws are math relationships of a couple properties. And these are the ones that we're going to focus on. This is the amount, that's concentration. This is volume. So going back to a container, here is a closed container, and it contains a whole bunch of particles that are bouncing around. You then have something called pressure, and pressure is the particles, it's the sum force of particles bouncing against the surface. So here's the surface of the inside of the container, there's the particle, and as it hits, it's going to apply force, and the sum forces of all of the particles bouncing against the walls of the container, that is pressure. So here is one way to mathematically define pressure. It's the force of all the bouncing of all the particles over the entire area of the container. So all the sides of the container. Now, there's other formulas for determining pressure, so it's got a whole bunch of other units, and we'll get into those as well. So this summarizes these terms. You already know about temperature. Temperature is movement, so that's how fast the particles are moving within a closed container. Now, big thing we're going to be looking at is the location of the gas. You have a closed container, which is what you see here, and then you have an open container. You can see this open container right here. If we go ahead and we shrink down here, here we have liquid mercury, and then we have a whole bunch of gas particles that are floating around. Notice there is no container, so they're free to bounce around wherever they want. Matter of fact, here's planet Earth. The only reason gases just don't fly off into oblivion is because of gravity, and that keeps the gas particles constantly coming back down to Earth and bouncing against the surface of the planet. The bottom line is we have gas and it's applying a pressure thanks to gravity, forcing it coming down. Now, when we look at pressure in an open container, such as the atmosphere, we need a way of measuring it. So here I'm drawing gas particles, and I just said that they're forced down by gravity and they're applying a pressure. So that's due to the force of the particles bouncing against this liquid substance that we see in this container, or in this open glassware right here. Now, this liquid substance is called mercury. It's pretty much the heaviest liquid at room temperature that we have on the planet. It's the heaviest substance. And what happens is, if we have an inverted tube, and the inverted tube has no gas inside, so it's in a vacuum because there's no gas, and the outside is facing the atmosphere, the gas particles will go ahead and slam down on the mercury and push the liquid mercury up the vacuum tube. Now, the more particles that are present, the more pressure applied, and the higher the liquid rises. The less particles that are present, the less pressure pushing down, and the lower the liquid rises. Now, the amount of pressure pushing down is determined by the height of the liquid mercury going up. So to make our lives a little bit easier, we made a standard where 1 atmospheric pressure, known as 1 atm, is going to be equal to 760 millimeters of mercury. So millimeters is the height that the mercury is being pushed up. So this is considered one standard atmosphere. Now you'll notice I have an equality here, and if I wanted to, I could go ahead and do a conversion. So for example, doing the question down below, I could do 3.03 ATM. 1 ATM is on bottom. 760 millimeters of mercury is on top. And then we're able to convert from atmospheres to millimeters of mercury. And notice millimeters of mercury is length. So these units are different from this pressure unit in a closed container that we see right here. So that could be, in this one, could be like newtons per centimeter squared. So we have different types of pressure units, especially depending on the environment. The last one is Torr. Torr is after Torricelli, not Torres, I wish it was. But it's named after Torricelli, who did a lot of pioneering work in gas chemistry. So notice 760 millimeters of mercury is equal to 760 torr. So make sure you know this equation. Yes, this is a measured value, so this has 3 sig figs, and that's 1.00 has 3 sig figs. All right, let's move on. Now we're going to get into gas laws dealing with closed expanding container. So let's go ahead and take a look at this container. To use an analogy, as we're probably all going to experience this closed expanding container at some point in the next year. This right here is a syringe, and this shaded area is the volume of whatever substance we have, depending on how far that volume has been pressed in the syringe. So using the syringe analogy, pretend that this is the needle, this is the area. Instead of containing a liquid, it contains a gas. And this is going to go up or down. So notice, even though it's a closed container, it can expand from being a small volume to being a high volume. Let's go ahead and take a look at the animation for Boyle's Law. So in this instance, I have that same type of closed expanding container. So this cylinder right here, notice I am decreasing the volume. And as I do it, the particles are smashed close together, and consequently there's a lot more bouncing going on by the particles. So more bouncing against walls of container mean a higher pressure. So looking at my my mouse icon arrow that's moving around, as I increase the volume, you'll notice over here I decrease the pressure. So they have an inverse relationship. Now if you take a look at this data table down here, it just kind of summarizes the movement. Now if we wanted to, we can go ahead and plot a graph relating pressure and volume. So here I'm plotting an increase in volume results in a decrease in pressure. So you can see the movement. So it has an inverse relationship. The next thing I want to point out too is I never touched the temperature. Now there's an implied Bunsen burner underneath that can heat it up if it wanted to, but instead the temperature is constant. And in this instance, it's held at a constant room temperature. So it's around 298 Kelvin. So know the relationships of pressure and volume. Pressure and volume have an inverse relationship. So if you increase the pressure, then you're going to decrease the volume. So the volume went from 8 to 4 as you increase the pressure. Memorize this equation right here. This is a pretty easy calculation to do. All you got to do is just plug and chug. Over here is the initial pressure and volume. So here's my initial pressure, here's my initial volume, and then here is my final pressure and my final volume. I'll give you a paragraph very similar to this on a future quiz or exam. You'll then have to plug in the values. So put a volume here, put the pressure here, and then you'll have to solve for an unknown. So one of these is going to be your algebraic x. You have to solve for the unknown. In this case, maybe it's going to be volume. So what is the volume if the pressure is increased to 770 millimeters of mercury? And then you simply solve for x. So here's the calculation. Same calculation, just showing you the setup. Yes, all of these are measured, so it should be 3 sig figs. Notice the volume is completely ignored because it doesn't change. And it says there, the volume does not change. This is a big hint that we're using Boyle's law equation. So here's another problem. In this case, we're solving for what is the pressure if the volume is decreased to 1.25 liters. And so you have to plug everything in. You have to rearrange it like you learned in your math class, and then solve for the unknown. In this case, the final pressure. Now I'm planning to keep the pressure in millimeters of mercury. And I'm planning to keep the, although I could change it to atmospheres if I wanted to. But I like millimeters of mercury. So all options are on the table. As far as volume goes, I plan to keep it in liter units for right now. Now we're going to get into Charles' law. Before, we focused on pressure and volume, and I remember making a big stink that temperature is constant. Now, temperature is going to change. Temperature is going to go from some initial temperature, to a changed final temperature. So if we take a look at our picture to the left, we adjust we have an invisible Bunsen burner that's underneath, and it's changing the temperature, aka the movement of the gas particles. So here it's at 150 degrees Kelvin. So notice I increase the Kelvin, aka movement, from 150 to 300, and what it does is it increases the volume. And it goes from 4 liters to 8 liters. As far as the relationship goes, the volume increases if the temperature also increases. And this is assuming that pressure does not change. Pressure is constant. Matter of fact, that's the big hint that you have to use Charles' law. So make sure you memorize this. This simulation. Now I'm just going to go ahead and click over to Charles' law. Now we're just looking at volume and temperature. Pressure does not change. So if I wanted to increase the temperature, there's an invisible Bunsen burner underneath. Then I'm increasing the volume. Now the volume changes actually because of the pressure of the particles. But as the volume expands, then the pressure equilibrates back to what it originally was. So the pressure doesn't change. But bottom line is, pressure doesn't change for Charles' law. And then you'll notice if I start adding in data, the graph has a straight line because it's a direct relationship. So let's go back to the calculation. Here's the setup. You have to solve for your unknown. Make sure you review your algebraic rearrangement. That'll make your life a little bit easier. And a big hint, if you ever see something like this, the pressure doesn't change, then you know that you're dealing with Charles' law. And you have to use the proper equation, which is this one right here. Now, one thing you have to do is if I give you Celsius at any time, you have to change to Kelvin, because I want you to be comfortable with temperature conversions. Now, I'm only going to do this with Celsius. I wouldn't give you Fahrenheit, but I would give you Celsius, because it's very easy to go from Celsius to Kelvin. You simply add plus 273. So notice the Celsius is turned into Kelvin. Oops. Actually, this one right here, 273 plus 25 is 298. And then 30 plus 273 is 303. And here's your final answer. Yes, all of these are measured values, so should be reported to those 36 figs. So here's another example. And then the last one is the combined gas law. So this is when we combine everything. We combine pressure, temperature, and volume. So everything changes. Mathematically, it's still pretty straightforward. You're simply going to plug in all of your values, although change Celsius to Kelvin, and you're going to solve for the unknown. What I recommend is rearranging all of your variables ahead of time before you start putting in values. So that'll make it just a little bit easier. So in this case, they want to know what is the final volume. So here's my P1, V1, T1, P2, V2, T2. They want to know what the final volume is. So I need to start rearranging, and I just rearrange with the variables without putting in the actual numbers yet. So in this case, I need to multiply both sides by T2. That gets rid of the T2 on the bottom. I then need to divide both sides by P2. That gets rid of P2 on the bottom. And then you'll have T2, P2 times T1, P1, V1, and then you can start putting in your individual numbers into these variables. So I got 1.51 liters after I worked out the first problem using that little rearrangement trick. Now if I kept the units in there, everything would cross cancel, but I kept them out there since I've already double checked it by cross canceling out the original variables. So that's something that you should do. Another trick I want to teach you is you really only, let's try it again. You really only need to memorize the combined gas law. And then if something says, for example, in Boyle's law that temperature is constant, then automatically you can cancel out each of the temperatures, and then voila, you have Boyle's law. On the other hand, if it were to say, oh, pressure is constant, then you could cancel these out, and then you would have Charles' law. So that makes memorizing these equations a little bit easier. All right, so now we're going to go back to a closed container where it doesn't change volume. And this is what we call the ideal gas law. And technically, everything is going to be ideal in this class, but the ideal gas law refers to this equation right here, which you have to also memorize. Ideal essentially means we're going to be taking shortcuts to make the math easy. So when something is ideal, it doesn't exist in the real world. It's a simplified version just to make our math and our lives easier. So in our ideal settings, we're going to assume, even if it's not real, all collisions are going to be perfectly elastic. They're going to bounce perfectly. And there's no attractive forces or cohesive forces from electrostatics. We're going to assume that all gas particles are going to be completely bouncing around regularly. There is no cohesive forces. It's only disruptive from temperature. And if we assume that, then we can make this nice relationship. Assuming we have a closed container where the volume doesn't change at all and it's not exposed to the atmosphere. Here we have a couple particles that are moving around, and they're bouncing against the inside of the container. We can assume that the pressure from the total bouncing of the particles against the volume of the container is going to be equal to the number of moles, that's the concentration of the particles that are bouncing around, times the speed of the particles, also known as temperature. So temperature is movement, and the faster the particles are bouncing around, then the higher the pressure inside the volume. But it's going to be equal to the moles times the movement of the particles. Now, this R allows us to convert from one type of unit to another. So pressure and volume is going to be atoms and liters, and then N is going to be moles, and then temperature is going to be kelvins. So it allows us to convert these units into these units. This conversion factor we call a gas constant because it doesn't change. Now this is ideal settings, which isn't real world, but math-wise it makes our lives easier. So you could even memorize this gas constant because it doesn't change, like Avogadro's number or molar volume, which we're going to get into later. So make sure you understand the concepts of the particles bouncing around. Again, it's the pressure from the particles bouncing inside a volume of container. That's equal to the number of particles as well as how fast they're moving or the temperature. Here is a calculation I could have you do. Very straightforward. You're simply going to plug in these values. Moles, pressures for atmospheres, temperature in Kelvin, you have to do a conversion, and then you'd have to solve for the unknown. Again, you want to do a rearrangement ahead of time. So for example, here's P1, V1, N1, R1, T1. There is no before and after. This is a closed container. So we're just going to have to rearrange for what we need. In this case, we'll go for volume. We divide both sides by pressure. And so it's going to be nRT. And then pressure is going to be on the bottom. Here is the worked out equation. after I rearranged the equation, solving for volume. I did write the units in here. You don't have to do that. I just wanted to prove to you why we have the gas constant. Because with the gas constant, the moles cancel out, the ATM cancels out, the Kelvin cancels out, and then it leaves the desired target unit. So make sure you also have this one memorized. And let's move on to another one. Now this one's going to be really easy. This is called Dalton's Law. Essentially, we're going to have a closed container, and it's going to contain a mixture of gases. In short, Dalton's Law is the total pressure of a mixture of gases is equal to all of the individual gases. And the individual gases, it turns out, nature's an accountant, and it keeps track of all of the pressures. We call these partial pressures. So these individual gas pressures, it turns out, equal the total mixture gas pressure. That's pretty cool. So memorize this type of equation. I'll give you like 2 or 3 gases. You simply have to add them together, and then that equals the total. So in this case, here we have a partial pressure for a single substance such as oxygen, that's 1. Let's say that's nitrogen, that's 3. Let's say that's carbon dioxide, that's 2. And so therefore, when I add all of these together inside one container, the total for the mixture, which happens to be air, is going to be 6. Now, I'll probably be a little bit tricky. So instead of asking for the total, maybe I'll ask you to do some algebra and solve for a partial pressure. So for example, I could give you a total, which is 742. And then here are the partial pressures for nitrogen, oxygen, and water vapor. So nitrogen is 581, oxygen is 143, and then you have to solve for water vapor, which is X. So my calculation is going to be 18 millimeters of mercury, and then this is going to be for water vapor. It's a gas. So make sure you have that memorized. Now we're going to get into molar volume. To investigate molar volume, we first have to take some shortcuts. So this is all going to be ideal settings. Remember, ideal is not real, but it makes our lives easier, and so we love it. So first off, it has to be an ideal gas, similar to the properties for the ideal gas law. So for example, perfect bounce, all disruptive forces, i.e. through temperature, no cohesive forces at all. It has to be elastic. We also need to go ahead and make sure that we have a standard temperature, which is 0 degrees Celsius, or 273 Kelvin, and a standard pressure of 1 atm, or 760 millimeters of mercury. So if we have this standard temperature, pressure, and it is an ideal gas, then we can make this assumption that if we were to sit there and fill up a balloon with 1 mole of any gaseous substance, it will fill up the balloon to have a volume of 22.4 liters. So think of a pretty large gallon of milk. That's around the ballpark of 22.4 liters. So this is really cool. Just like Avogadro's number, where 1 mole is always equal to 6.2 to the 10 to the 23rd, 1 mole of any gas is always going to equal 22.4 liters. So here we see different balloons. Notice it does have to be at 1 atm, 273 Kelvin. But again, if I were to have 1 mole of the helium, it's 22.4 liters. 1 mole of oxygen, 22.4. 1 mole of nitrogen is 22.4 liters. So we have a nice equality. 1 mole is equal to 22.4 liters. And now we have conversion factors. And what do we love to do with conversion factors? Well, anything with moles, then we like to do conversions. So I could give you a problem like this, where I have 2.75 moles of N2 gas. STP means standard temperature pressure, and it's ideal. Then automatically you can use the molar volume equality. Here's your starting value, 3 sig figs. Starting value is always measured. And then moles goes on bottom, liters goes on top. Yes, this is also measured, so it has to be, so you count the 3 sig figs. And then here is your final volume of the gas at STP. So you can do that for any substances and anything that has moles as a gas. So here's some other, this is a gas right here, methane, stuff we have in Bunsen burners to make them burn. So in this case, we started off with grams. So using stoichiometry, you already learned. Learning what the molar mass is, you have to go from grams to moles. And once we're in moles for the gas, and it's STP, then you use the molar volume. Moles goes on bottom, cross cancels, leaving the volume liters on top. There's our final answer. 3 sig figs, 3 sig figs, 3 sig figs. Final answer is rounded to 3 sig figs. Let's do the next one. How many grams of helium are present in 8.00 liters? So in this case, we start off with liters of gas at STP. So now we have to use the molar volume to convert from liters to moles. Once we're in moles, we can go to grams using the molar mass. If we wanted to, we could also go to molecules, or just keep it at moles. So there's the grams for that one. And then if you have a balanced equation, yay, then we can use it in a balanced equation. So in this case, we want to go ahead and we're starting with grams of aluminum right here. And then we need to have a gas that's in the equation. In this case, here's a gas, oxygen. And assuming we're at STP, we can convert from the grams of aluminum to the liters of oxygen for that gas. And that's how many liters you would actually need of that oxygen for this reaction to occur, given the 15 grams. So molar mass to start off with, grams to moles. Here we have that mole ratio taken from the coefficients. And then once we're in moles of O2, then we can go use the molar volume to go from moles to liters. So make sure you practice those problems. Here's another problem, just like it. Liters using molar volume to go to moles. We then use a mole ratio from the balanced equation, and then moles to grams of our target substance. Again, be sure to practice these, and that concludes our gas laws commentary.